Welcome to lecture number 11 of the course. Let us recall what we have done in the previous lecture. So, in the previous lecture we talked about various sources of nonlinearities. There are primarily two: material nonlinearity and geometric nonlinearity. So, material nonlinearity stems from the nonlinear stress strain relationship, right. In the language of structural analysis, we can call it nonlinear action deformation relationship. And then we talked about geometric nonlinearity, which basically comes from the considering the equilibrium in the deformed position. So, that gives you nonlinear RS relationship, and the nonlinear compatibility, which gives you nonlinear VR relationship. So, how you consider these different sources of nonlinearity, based on that we can perform different levels of structural analysis, right. So, in the last lecture we started talking about various levels of structural analysis. So, we will continue with that in this lecture. So, let us get started. So, in the last lecture we talked about elastic first order analysis. We talked about this elastic first order small displacement analysis. Okay. Please refer to the previous one. So, the idea, just to briefly review it, in the elastic first order analysis, it is a small displacement analysis and we exclude all sources of nonlinearities, right. So, force deformation or action deformation relationship is linear, equilibrium is considered in the undeformed position. So, that means the RS relationships are all linear. Displacements are assumed to be vanishingly small for compatibility, that means the VR relationships are also linear. Okay. So, therefore, the resulting force displacement relationship for a structure is also linear, and this is generally good for structures under service loads. So, on this figure which I have introduced to you in the previous lecture, so if I look at this building, okay, and if I do a elastic first order analysis, let us say this is the gravity load P on each floor, and then you have a lateral load H, which is a fraction of the gravity load, and that coefficient is alpha, right. So, if I do an elastic first order analysis, then the relationship between the applied force H and the horizontal displacement delta is basically a straight line, right. This is the elastic first order analysis. Then in the previous lecture we started talking about the elastic critical load analysis, and I have defined what is meant by critical load. It is the critical load is the load at which both the original and an alternative loading path becomes mathematically valid. So, it is called bifurcation of equilibrium. So, we will talk little bit more about this. So, what we do in this analysis, the force deformation response is linear, equilibrium is considered in the deformed position. So, RS relationships are nonlinear, but the displacements are assumed to be vanishingly small for compatibility. That means, the VR relationships are all linear. So, we determine the critical load using an eigenvalue analysis, and the eigenvectors gives us the shape of in the post critical state. Okay. So, let us review little bit some concepts of a stability, which you may have done in your mechanics of solids class. So, let us say if you take a football and cut it into two and take a small cricket ball and put it inside it. Okay. So, that is what I am trying to show here, right. Now, if you move the cricket ball little bit, disturb it and release it, what happens? It will oscillate and eventually come back to its original equilibrium position. Why? Because when you take this and move it to here, right. So, at this position the weight is acting downward, and this is the normal reaction N, okay, normal to the tangent here, right. Now, the resultant of the two is the driving force, which drives the ball back to the equilibrium position, static equilibrium position, right. So, eventually it may oscillate and then come back to the original position, right. So, this is called stable equilibrium, and how we define a stable equilibrium? We say a system is said to be in stable equilibrium if for all possible geometrically admissible small displacement. Geometrically admissible means that the displacement must be consistent with the constraints that are present in the problem. Okay. So, for all possible geometrically admissible small displacements from the equilibrium configuration, restoring forces arise which tend to accelerate the system back towards the equilibrium position. So, this is what is happening in this case. So, we call it a stable equilibrium. Okay. On the other hand, consider this case. So, you take the same football that you cut it into half. Now, put the convex side up and put a small cricket ball here. Then what happens? If you disturb it little bit, okay, so let us say the ball is here. So, at this stage the weight is acting downward and this is the reaction, and the resultant of the two is like that. So, this force is actually going to take the ball away from the equilibrium position. So, this force is the upsetting force, whereas here this is the restoring force. Okay. So, therefore, this equilibrium is unstable. On the other hand, if you take the same cricket ball and put it on a flat surface, okay, so what happens here? This is at this position, you move it a little bit away, okay, then the weight is acting downward, the normal reaction is upward and it is in equilibrium. So, there is no change. So, we call it a neutral equilibrium. Okay. So, just to give you an example of this, so consider a rigid bar. So, this is a rigid bar which is pinned here at this point, right. Now, if I apply a vertical upward force P as shown in the figure, and then let us say your friend comes and disturbs it little bit. So, moves it to the right. Okay. So, the force the displacement is like that. Okay. So, then this force P is acting like this. So, the moment you remove that disturbance, what is this P force doing? The P force is applying a restoring moment P into delta. So, that is what I am showing here. So, this P force is applying a restoring moment to bring it back to the original equilibrium position. So, this is an example of stable equilibrium when the load is tensile. Okay. As you can see in this case, it is upward. Okay. On the other hand, if I take this load to be downward, right, and then if you displace it a little bit, right. So, then there is a moment P into delta, this P into delta. Okay. Now, this is an upsetting or overturning moment. So, what this does, this moves the bar away from the original equilibrium position and it will never come back. So, this is an example of an unstable equilibrium for compressive load. Okay. So, now let us talk about an example of how we do critical load analysis, elastic critical load analysis. So, this example you have seen before. So, we have a rod, rigid bar or rigid rod, okay, which is connected to a spring like that, okay, and then I am applying a vertical load P. Okay. So, as I said earlier that we have to consider the equilibrium in the deformed position to determine the elastic critical load. So, what I am doing, I am moving this away from this equilibrium position. So, moving it to this position, right, and then the force P is acting like that. Okay. So, there will be a reaction, vertically upward reaction P at point A, and then since I have moved it to the right, then because of this displacement delta which causes delta deformation in the spring, then the force in the spring is going to be K into delta. Okay. And what is delta? Delta is this displacement. Now, if I consider the displacement to be small, and that is what we said, for elastic critical load analysis, displacement is vanishingly small for compatibility, meaning that if this theta is small, then this can be written as simply h the height times the theta. So, this delta is equal to h times theta. Okay. So, if that means this force becomes K into delta is equal to K into h into theta. So, then there will be equal and opposite reaction at the base. Okay. So, now I want to write down the equilibrium equation. So, what I can do? I can take moment about this point because summation Fx, summation Fy are already 0. Okay. So, if I take moment about A, then what do I get? I get P into delta, that means h theta, minus this force times this lever arm which is h. So, k h theta into h. So, that is k h square theta is equal to 0, right. Now, theta is non-zero for a non-trivial solution. If theta is 0, then you do not get anything, right. So, for a non-trivial solution, what we do, theta is not equal to 0, that means P h is equal to K h square. From there, what we get, P is equal to K h, and we call it the critical load. Okay. So, if I show the equilibrium path, my vertical axis is the p and the horizontal axis is the delta, or you can also plot theta. So, as I keep on increasing the load, right, I am going along this path, meaning that there is no horizontal displacement, right. Or in other words, let us say when you are here, if you apply a little bit of disturbance and remove the disturbance, then the bar will come back to, so let us say you move it, it will come back to the original position. Okay. Up to this point. So, up to this point it is called the stable equilibrium. Okay. Now, at this point when the load becomes kh, okay, then if you displace it, it will remain in equilibrium in that position, right. If you displace it a little bit more, it will again remain in equilibrium in that position. So, we call it, that is the neutral equilibrium, which is indicated by this line, and this load is the critical load denoted by PCR is equal to kh. Okay. Now, imagine if you keep on increasing the load further beyond kh, beyond PCR, then what happens? Then if you apply a slightest disturbance, then it is going to collapse. It will never come back, but will keep on moving. So, that is called the unstable equilibrium, right. So, therefore, the critical load is of interest, because beyond which you cannot get it in reality. Okay. And in reality also there are other things that I will talk about. Okay. So, this point is called the bifurcation of equilibrium, because from here you can see this is the alternate loading path. It was going vertically, there was no delta, but then all of a sudden it can go to the right or it can go to the left. So, therefore, it is called the bifurcation of equilibrium. Two alternate load paths are possible. Okay. So, now let us take another example of elastic critical load analysis. This also you might have done in your mechanics of solids class. It is the Euler buckling analysis. So, we consider an ideal column with pinned ends. Ideal means the column is perfectly straight, the material is linearly elastic, that means the material follows the Hooke's law, and I apply the force P at the centroid of the cross section. So, let us say this is my ideally straight column. Okay. I am applying this P force at the centroid of the cross section. Okay. So, let us say I can draw the cross section something like this. So, this is cross section, I am applying the load at the centroid, okay, or it could be the other way around, it could be rotated. Okay. And then x y, the plane that I am showing here on the figure. So, this is y and this is x, is the plane of symmetry. This is cutting the column into two symmetrically. Okay. And any bending takes place in this plane. So, that means it is going to bend like that. Okay. So, this is our deformed shape, and we will consider the equilibrium in the deformed shape. So, how do we go ahead? So, if I cut it here, if I cut it somewhere here, then what happens? Well, you will have this reaction here. So, if P is there, then there is, this is the P reaction here. Okay. And then when you cut it here, there will be a moment, the internal moment, right, and there will not be any shear, because in this position, okay, you have P, they are in equilibrium. So, there is no shear force, this is 0, shear force is 0. So, that means there is no shear and there is no shear force here. Okay. So, now what we can do? We can write down the equilibrium equation. So, what is the equilibrium equation? If I take moment about this point, then this m internal is producing a counterclockwise moment. So, therefore, I am writing minus m internal, and then P into V is producing a clockwise moment. So, plus P into V is equal to 0, and we all know the moment curvature relationship, which is m internal is minus E I d2 V dx2. So, that is indicated by V double prime, and note that this minus sign comes depending on the sign convention and this coordinate system that you have taken. For me, the y axis is to the right, x axis is to the upward positive, and my displacement V is positive to the right. So, therefore, I am getting a negative sign here. Okay. So, if you substitute this here, then what you get, E I d2 V dx2 plus P V is equal to 0. So, this is nothing but a second order linear ordinary differential equation. Okay. So, the solution takes a form V is equal to A sin kx plus B cos kx, where k square is equal to P by E I. So, if we satisfy the boundary condition at x is equal to 0, the displacement is 0. At x is equal to L, again the displacement is 0. Then what we get is this equation sin k L is equal to 0. Remember, k square is equal to P by E I. So, from here we can get the Euler buckling load or Euler critical load, which is pi square E I over L square, and we also get the displaced shape. Okay, not the magnitude, we get the shape, only the shape. Okay. So, that is A into sin pi x by L, where A is a constant. Okay. So, that is how we do the Euler buckling analysis. So, if I again show you the equilibrium path for small displacement response, so where V is, let us say, the displacement, I showed V at anywhere, okay, but I can plot it the displacement at the center of the beam. Okay. So, for small displacement, this is my stable equilibrium path. Okay. And from here you have the bifurcation of equilibrium, you get the neutral equilibrium, this is the Euler critical load and this is the unstable path. So, in other words, if I write that P less than PCR, then this is stable. This is stable equilibrium. If P is equal to PCR, then it is neutral equilibrium, right. If P is greater than PCR, then this is unstable, right. That is what we get. Okay. Now, what we can do, we are interested, let us say, in the stress. So, I can calculate the critical stress, which is the critical load divided by the cross sectional area of the column, okay, PCR by A, and PCR I have already determined pi square E I over L square. Now, here I am writing, instead of L, I am writing K into L, where K is the effective length factor, because we have looked at only pin column, but if I take a different boundary condition. So, let us say if I, instead of taking pin, I take fixed column. Okay. So, if I take fixed column, then it goes like this. Okay. So, the effective length is basically this much. Okay. So, the K effective length factor becomes 0.5. Okay, and so on for other boundary conditions, right. So, now I can rewrite this equation, I can rewrite this, just replace the moment of inertia I with radius of gyration I is equal to A r square, then I will be getting pi square E by K L by R whole square. So, I can plot this sigma shear. So, sigma shear versus K L by R, this is the Euler buckling curve. Okay, that you have seen in your mechanics of solids class. So, if I do an elastic critical load analysis with reference to this figure, where the horizontal loads are not present, okay, then you get something like this. This is the bifurcation of the equilibrium. Okay. So, this load is the PEC, the elastic critical load. There are different notations people use, PEC, PCR, PE and so on, but they all mean the same, the Euler critical load. Okay. So, now let us talk about inelastic critical load analysis. Okay. So, I have shown you the Euler critical load, let us say this is the stress P by A. Okay. You can call it the critical stress, but right now let us call it simply the stress, the force divided by area. So, this is the curve for the Euler buckling. Okay. So, this is my sigma CR. This is the curve sigma CR. Okay. Now, if you recall that the Euler buckling is for an ideal column where the material follows the Hooke's law. That means, the stress and strain are proportional. Okay. So, consider this curve is going like that, okay, going up, but it cannot exceed the yield strength of the material. So, when it reaches the ultimate strength, it could be yield strength, could be ultimate strength, we will talk about it. Let us say this is the strength limit, right. It cannot exceed the strength limit. Okay. So, then it will fail by crushing. Okay. There will not be any buckling, right. So, we call this the short column. So, in this range, the columns, the slenderness ratio in this range, we call them the short column. They will never fail by buckling, they will fail by crushing. Okay. On the other hand, when the stress is below the proportionality limit sigma PL, okay, then they will fail by elastic buckling. Okay. So, we call those columns the long columns, right, because the stress has to be below the proportionality limit for the Euler critical load analysis to be valid. Okay. So, now as you can see, between sigma PL and sigma U, that is the ultimate strength, you have quite a bit of range, and there are slenderness ratios of column which can lie in this range. So, what happens there? The stress is above the proportionality limit. Okay. So, here what happens, the column undergoes inelastic buckling, right. So, that is what is indicated through this curve. So, this is called the inelastic stability limit or inelastic critical load. Okay. So, here in this figure I am showing, the sigma PL, the proportionality limit, and if I want to determine this critical slenderness ratio, what I can do, how do I calculate the critical slenderness ratio? I will simply substitute sigma CR is equal to sigma PL. Okay. And what is sigma CR? If you go back to the previous slide, sigma CR is pi square E by KL by R whole square. So, if you substitute that, pi square E divided by, now KL by R, in this case I am simply writing L by R because I have taken this figure from the book Mechanics of Solids by Gere and Timoshenko. Okay. So, there it is simply written as L by R. So, I will also write L by R because you can always incorporate the effective length through this factor K. Okay. So, pi square E by L by R whole square is equal to sigma PL, right. From here I can calculate what is the critical value of this slenderness ratio. So, that is basically given by this. From here I can directly write L by R is equal to pi into square root of E by sigma PL. So, consider a steel with proportionality limit sigma PL equal to 250 MPa and the modulus of elasticity equal to 200 GPa, then this L by R critical slenderness ratio can be calculated easily, and it turns out to be 88.9. So, the column which are between this and this are basically intermediate columns, and they will fail by inelastic critical load. Okay. There are primarily two theories for inelastic critical load analysis, and in this course I am not going to get into the details of the theory, okay, but nevertheless I will mention. So, one is called the tangent modulus theory, which was proposed by Engesser in 1889. Okay. So, if I show you schematically, for an ideal inelastic column, if I plot the force P, axial force P and the lateral displacement V. Okay. So, if it is elastic analysis, then this is the Euler critical load. If we go by the tangent modulus theory, then this is the tangent modulus load for small displacement. Okay. And then in 1895, Engesser revised the theory and developed the reduced or double modulus theory. So, according to which the inelastic buckling load is the reduced modulus load, which is larger than the tangent modulus load, right. After a few decades, okay, Shanley developed a very simple column model to explain the concept of inelastic buckling and developed what is called Shanley's theory of inelastic buckling, which he has done in 1947. Okay. So, according to Shanley's theory, the bifurcation of equilibrium happens at the tangent modulus, which is Pt, and then it goes like this, and it approaches the reduced modulus load when the displacement becomes infinite, which is not possible in reality. Okay. So, buckling, the bifurcation happens at the tangent modulus load, which is Pt, and then it goes to the asymptotically approaches to the reduced modulus, but that cannot happen in reality because of so many other factors. So, actually real column shows a behavior like that. This is the behavior of real columns. If you are interested, you can read more in this reference too, that is the book by Gere and Timoshenko, the Mechanics of Solids, Mechanics of Materials. Okay. So, actual behavior of real column is something like this. If I plot the critical load and the slenderness ratio KL by R, okay. So, this is our well known Euler curve, but actual test data, the range of test data lies in this range, lies in this range. Why? Because of several things. Initial out of straightness or initial crookedness, that means the column is not perfectly straight. Whatever member you fabricate or you make, you roll, okay, there will always be some initial out of straightness. Eccentricity of the applied load, in theory we can say, okay, the load is applied exactly at the centroid of the cross section, but in reality it cannot be done. Okay. Then the presence of residual stresses. What is residual stress? I will talk briefly about it, and then there could be strain hardening. So, when I get into material nonlinearity, I will talk about what is meant by strain hardening. Okay. So, this is the behavior of actual column. Now, in design, what we do, there are several design codes that will give you how to determine the strength of a column considering all these factors, right. So, in this course we are not getting into the design, but I thought of giving you a sense of where this is kind of the range where test data falls. Okay. So, what is residual stress? So, residual stress, as the name suggests, it is the stress that remains in a member after it has been formed into a finished product. Okay. So, in structural steel shapes, those are hot rolled, uneven cooling after hot rolling is a major cause of residual stress in rolled shapes. What happens, when we roll, let us say I am showing here a portion of an I section, or in the US they call it wide flange sections. Okay. So, this is called the flange, this is another flange, and this is the wave, right. So, the compressive stresses developed in regions that cool fastest. When you roll it and let it cool, come to room temperature. Okay. So, what happens, the flange ends, that means this region, okay, and the middle portion of the wave, that means this regions cool faster. Okay. So, in those region you will have compressive residual stress, which is indicated by this. This is a pattern of residual stress that I am taking. Okay. The pattern could be different, but just for the demonstration. Okay. So, let us say this is my variation of the residual stress. So, in the wave here, this part is under compression. Okay. And for the flange, this part and this part, they are under compression because they tend to cool faster than the region which is, let us say, this junction here or this junction here. Okay. So, this junction cools at a slower rate, okay, which is obvious. So, in this case what will happen, the middle portion of flange and flange wave junction cool the slowest. So, you will have tensile residual stresses. So, in this is the tensile residual stress, okay, and here in this portion and here it is just behind, okay, you will have tensile residual stresses, right. Now, the pattern of the residual stress must be such that, let us say you have a steel member lying, right, there are no force acting, but there is residual stress at every section. What does it mean? That there are no forces applied to the member, that means the residual stress must be self equilibrating. That means the resultant of this, if you take the stress resultant, is must vanish, it should be equal to 0, no axial force, no moment. Okay. So, that is how the residual stress happens. Now, to explain this concept of residual stress, I will take a very simple example. So, let us consider we have got 3 identical rigid bars, steel bars, identical steel bar, that means same material, same geometry, everything the same. Okay. And these bars are connected by 2 rigid blocks at the ends, right. Then what I am doing, I am hitting this middle bar, from room temperature to some 1100 degree Fahrenheit, and then cooling it down back to the room temperature. The other 2 bars are remaining the same at room temperature. Okay. So, what happens if I plot the stress in the middle bar with the temperature, what happens? So, as I keep hitting the middle bar will try to elongate, right. But the outer 2 bars, they will not allow it to happen, right. So, there is a compromise, that means there is a compatibility. So, the middle bar will try to extend a little bit, okay, or it tries to extend due to temperature, but it will compress a little bit, the outer two bar will elongate a little bit. Okay? So, that is the compatibility, or you can say it is a compromise. So, what will happen? The middle bar will be subjected to compressive stress, okay, because it is trying to expand, but the outer bars are not allowing it. So, the middle bar will have a compressive stress. So, let us say we start at point A. In the vertical axis is stress in the middle bar and the horizontal axis is temperature. The right hand side vertical axis is basically also the stress, but in a different unit. This is MPa and this is KSI. Okay. So, we start at room temperature at point A, and as we keep hitting the middle bar, the stress in the middle bar keeps on increasing and we go like so. At point B, what happens, about 340 degree Fahrenheit, the middle bar yields, the material yields. Okay. Now, we keep on increasing the temperature. Then what happens? As we keep increasing the temperature, the yield strength of the middle bar will reduce, because that is the nature. Okay. If you take a piece of metal and keep hitting it, after some temperature, the yield strength of the material will start to fall. Okay. So, if I keep on hitting from this point, the force in the middle bar is restricted or limited by the yield strength, which is reducing. So, as I keep increasing the temperature, the middle bar goes, the stress in the middle bar goes like this. So, at any point, if I have a stress in the middle bar is, let us say, this value, what are the stresses in the outer bars? Is basically half of that, because we have got identical two outer bars and the same bar in the middle. Okay. So, for force equilibrium, the stresses in the outer bars must be half of that of the middle bar, but opposite nature. Outer bars are tensile, middle bar is compressive. Now, coming back. So, we are going like that, okay, and this is, let us say, 1100 degree Fahrenheit. From here, I decide to cool it down back to the room temperature. Then what happens? The middle bar will unload elastically. That means, this compressive stress in the middle bar will keep on reducing. Okay. Eventually, it will go into tension. So, this is my 0. Okay. So, eventually, it will go into tension, and then at some point at D, middle bar will reach its tensile yield strength. So, it yielded in compression at point B, and that continued here, and then at point D, it is now yielding in tension as I reduce the temperature. Okay. Now, what happens? From point D also I am reducing the temperature. So, this is at a higher temperature, right? This is at a higher temperature. If I reduce the temperature, the yield strength will keep on increasing. So, middle bar will continue to yield with increased yield strength, and when it comes to the room temperature, in this case, this is equal to the yield strength of the material at the room temperature. So, what are the stresses in the outer bar at this point? At this point, the stresses in the outer bar is equal to 50% of sigma y. So, outer bar will have sigma y by 2, but what is the nature? Middle bar is tensile, but outer bars are now the opposite, compressive. Okay. Now, what happens if you from any point between B and C, you actually reduce the temperature instead of from 1100 degree Fahrenheit. So, let us say if you reduce the temperature from this point, you will come back in a straight line elastically, and you will come to this point. Okay. What if you try to reduce the temperature from, let us say, 800 degree Fahrenheit from here, then you will go parallel, parallel up to this point until it reaches the yield strength in tension, and then from here it will go like that. Okay. So, what this tells us? What we have done? We have heated only one bar, the middle one, to some temperature and let it cool and come back to the same room temperature. And what we see that at the end, the middle bar is having a tensile stress, okay, which in this case happens to be the yield strength. Okay. And the outer bars have half of it, right. So, this is kind of an analogous to what we have seen earlier. Outer bars are always at room temperature. So, you can say, well, they are cooling faster than the middle bar, because middle bar was heated and then brought back to the room temperature. Okay. So, the middle bar is actually cooling slower, and it has a tensile residual stress. So, if I go back, what I said, that the region that cools the slowest, just like the middle bar, will have tensile residual stress, and the region that are cooling faster, in this case the two outer bars that were never heated, they have compressive stress. Okay. So, that is the concept of residual stress. Now, coming back to the figure that we are referring to. So, if we do an inelastic critical load analysis, okay. So, for this case this are 0, I am doing an inelastic critical load analysis, and let us say the slenderness ratio of the columns are such that inelastic critical load and will happen, or it will fail by inelastic buckling. Then it is somewhere here, it is much smaller than the elastic critical load, because remember the Euler buckling curve, Euler buckling goes like that, okay, and we are talking about inelastic buckling in this range, where the curve is kind of going like that. So, in this range the Euler buckling stress is much higher. So, in this case therefore, we are here, this is the inelastic critical load, okay, when there are no lateral load, right. So, I will stop here in this lecture, and in the next lecture we will continue from here and talk about the other levels of analysis. So far what we have covered first order elastic analysis, we have covered elastic critical load analysis, and then we have discussed very briefly, just introduced you to the idea of inelastic critical load analysis, okay, and we will continue from here in the next lecture. Thank you.